A cloaking device, that's funny. Sorry, I was making some toast, and it took a little bit longer than I thought. Okay. Salutations. Let's get started. So, last time, we talked about torque. So, torque is equal to F perp times R. Okay. Where if you have, where R is the distance from the pivot point to the location where the force is applied. And then F, so here's the force. There's some angle between them. It's the perpendicular component of that force. Okay. Counterclockwise torques are considered to be positive. Clockwise torques are considered to be negative. The net torque is simply the sum of the individual torques. This toast is so good. Oh my gosh. It's like the best toast I've ever had. We talked about the gravitational torque, which is equal to the perpendicular component of the weight times R cm. So the gravitational torque acts as if the weight force were concentrated at the center of mass. All right. We can also think about it as an integral of x times lambda dx multiplied by g. All right. So that was last time. This time, we are going to talk about something called static equilibrium. So static equilibrium means the object does not translate so translation means to move around without changing your orientation. So these are translations. Okay. And it means that the object is not rotating about any axis. Okay. So translation, okay, you can be translating without rotating. You can be rotating without translating. You can be translating and rotating. Or you can be not translating and not rotating. And if you're not translating or rotating, you're just perfectly still. Okay? So that's what static equilibrium is. So not translating means that the net force equals 0. Okay? Not rotating means that the net torque equals 0. So static equilibrium has both of these conditions met. Okay. So let's do an example. Oh, by the way, if something is in static equilibrium, if we think about something that's rotating, you would calculate the torque about the pivot point. Okay? But if you think about the pivot point, a pivot point is the only part of the object that is not moving. Right? That if you look at my finger right here, it's not moving. That part of the calculator is not moving as it rotates. But if something is in static equilibrium, if you think about it, every point is the pivot point because every point is not moving. So you can choose the pivot point to be wherever you want it to be. So you just choose the pivot point to be any convenient spot. Okay. So let's do an example. We have a uniform beam. I might be running out of ink here. Has, another pen here. BRB. So a uniform beam has length 5 meters and mass let's say 40 kilograms. It is supported at its left end, okay, and let's say 1 meter from its right end. Okay, so here's the picture. So you've got this beam. It's supported at the left end, and it's supported 1 meter from the right end. Okay, and so each of these supports is exerting an upward force. So I'll call this F sub L, and I'll call this F sub R. Okay. Calculate F sub L and F sub R. Okay. So the net force in the y direction has to equal 0. All right. So we have two upward forces, and we have one downward force, which is the 400 Newton weight force. So that is net force equals 0. That's our first equation. Our second equation is involving net torque equals 0. So I will choose the left end to be the pivot. Okay. Left end is the pivot. And so using F perp times R, all the forces are already perpendicular. okay, because R goes horizontally, and the forces are either up or down. All right? So I don't need to worry about sine theta or anything like that. If we look at the left force, it has an R value of 0 because it's acting at the pivot point. So this one exerts no torque. The gravitational torque acts from the center of mass, which is going to be 2.5 meters away from the left end. Okay? Because the gravitational torque acts as if it were concentrated at the center of mass. It's a uniform beam, so that means that the center of mass is in the middle. So the net torque is going to be the gravitational torque, which is going to be 400 times R, the distance from the pivot to the center of mass, which is 2.5 meters. And we can see that gravity would tend to rotate this beam in the clockwise sense around the pivot. So that's a negative net torque. And then we also have the force from the right support, okay, which pushes upward, which is a positive torque around the pivot. The size of that force is F sub R. And it is acting 4 meters from the pivot. Now, why isn't it acting 5 meters from the pivot? It's because this force is acting 1 meter from the right end. The total beam is 5 meters long, so that would be 4 meters away from the left end. Okay, so that has to equal 0. So this this first force, okay, or the right force can be calculated from this equation really easily. So 400 times 2.5 is 1,000. So we have negative 1,000 plus F sub R times 4 equals 0. So that says that F sub R equals 250 newtons. Okay, which we then plug in to this equation. So we have F sub L equals, or minus 150 equals 0. That says F sub L is 150 newtons. Okay, yay. So there you have it. So here's what I want to talk about next. Next, I want to talk about distributed loads. So for a distributed load, you are not given, so that might be, for example, a bridge that has cars on it. So the cars are exerting forces on the bridge at different locations. So you don't, so the you have downward forces acting all over the bridge. Okay, so that's what a distributed load is. And so if you have a distributed load, you'll be given the force per length. The force per length will be some function, will equal some f of x. All right. Now the units of force per length would be newtons per meter. So you can think about force per length as like the density of force. So if force per length has a really large value at a particular value of x, that means that there's a lot of force pushing down at that location. Okay. So if you have a distributed load, the total downward force the total downward force is going to be the integral of f of x dx from 0 to L, whatever the length is, okay? All right. Now, why is that? That's because the total force is going to be the integral of df, just like x is the integral of dx, right? The total force is the integral of df, okay? And if we multiply both sides of this equation by dx, we get that df is actually equal to force density times dx, okay? Then we also have a torque, okay? And the total torque due to the distributive load is going to be the integral from 0 to L of x times f of x dx. Okay? So why is that? Well, torque is going to be the integral of dt, just like x is the integral of dx. Tau is the integral of d tau. And the amount of tau is force times x. And then df is f of x dx. Okay? So that's the total amount of torque. So this is for a distributed load. So let's do an example. All right. We've got a let's suppose we have a wall, and that wall has a beam attached to it. And if you look at the way this beam is attached, it's pinned. So because it is pinned, it is free to rotate about that end. It can swing down, it can swing up. Okay. But the end of the beam can't move, it can't translate. So this is allowed, because of this pin, it's allowed to rotate freely, but not translate. Okay. So basically, this pin can exert a force on the beam, but no torque on the beam. Okay, so in mechanical engineering, you often have these types of situations where one thing is joined to another in a certain way where there can be a force but not a torque. So if I take this knife, for example, if I hold it like this, I'm obviously exerting a torque on the knife, because if I didn't exert a torque on the knife, gravity would cause it to swing down vertically. So if I hold the knife like this, it can swing. So I'm exerting a force on the knife but no torque because it can rotate freely. But if I hold it like this, I'm exerting a force and a torque in order to keep it upright. All right? So there's different ways you can join things together. And then there's a string, okay, that is holding the other end and keeping this beam horizontal. All right? So there's this angle here. Okay, and so we're going to call the force, there's a force from this pin here. I'm just going to call that R. Okay, and it's a vector because, yeah, it's a vector. We're going to take our pivot point to be right there. Okay. And we are going to assume that there is a downward force on the beam. This is the downward force density on the beam, and it's given by 4 plus 5x. Actually, let's say 4 plus, how about 3x? Okay, and let's say that the beam is 1 meter long. Okay, so what we want to do is we want to calculate the reaction force and the tension, assuming static equilibrium. Okay, so the first thing you want to do is you want to evaluate these integrals. Okay, so what does it mean to say that the force density is 4 plus 3x? Well, that's a linear function, so it means that there's more downward force as we go away from the pin. So that must mean that the beam is getting thicker, or it's made out of a heavier material, or it has more stuff out here than it has over here. Okay, so we do these integrals so that the total downward force due to the load, okay, so we would say that the load exerts this sort of downward force. So the total downward force due to the load, by the way, let's make this angle 30 degrees for simplicity, is going to be the integral of 4 plus 3x dx from 0 to 1. And that is going to be equal to, let's see, 4 plus 3/2. So that is, the total downward force is 5.5 newtons. Okay. And then the total torque due to the load is going to be the integral from 0 to 1 of x times that, so 4x plus 3x squared dx. And that is going to be 2 plus 1. Yeah. So that's going to be 3 Newton meters. And I should keep in mind that this is a downward force. So the torque is actually negative 3 because a downward force would cause this beam to rotate in the clockwise sense. So that's a negative torque. And the force is also downward. Okay? So this is the torque, and this is the force due to the load that is due to stuff sitting on this beam. Okay? So now we have to have the net torque is equal to 0. Okay? So I know that the torque is going to be the torque due to the pin plus the torque due to the load plus the torque due to the rope. Okay? Now, if we look at the torque due to the pin is exerting a force at the pivot. So it has 0 for R. So the torque due to the pin leaves. All right? The torque due to the load is minus 3. And the torque due to the rope, well, the rope is pulling 1 meter away from the pivot because it's a 1 meter long beam. Okay, and the perpendicular component is going to be T sine of 30. Okay, so that's F perp times R for the rope, and it's pulling it in the counterclockwise sense, so that's a positive torque. All right, so sine of 30 is 1/2, so we get that the tension is 6 newtons in the rope. Okay, but we also want to find the reaction force. Okay, so in particular, the net force in the y direction has to be equal to 0. All right, so what are the forces? That we've got a force from the pin in the y direction. We've got the force from the load in the y direction. And we've got the force from the rope in the y direction. Okay, so we have 0 equals r sub y plus the force from the load in the y direction is negative 5.5 newtons. And then the force from the rope is, that's the y component of the force from the rope, my bad, is going to be T sine of 30, which is 3, okay? Because the tension is 6, sine of 30 is 1/2, so that gives us 3. So that tells us that the y component of the force from the support is 2.5 newtons. Okay? Now we want to get the x component of the force from the pin. Well, the net force in the x direction also has to be 0. This force right here is the downward force on the beam due to the load. Okay, so there is no horizontal force on the beam due to the load, due to the stuff that is sitting on top of the beam. Okay, so all we have are r sub x, and we have the horizontal component of the tension, which is pulling to the left, so it has a negative sign, and it's going to be T cosine of 30. Okay, so if you solve this, you get that the x component of the force from the pin is 6 times cosine of 30, which is 5.2 newtons. All right, so yeah, you get a force from the pin in the x and y direction, and you get a force from the tension, and that will put this beam in static equilibrium. Now, what if you found that the rope can only withstand 5 newtons? Okay, so this is used in engineering design a lot. So you say, you do the calculation. You say, I think that the load function is going to look like this. You set up your scenario. You calculate what the tension would be. All right. Then you choose the type of rope that you're going to buy based on the size of that tension. So you need to buy a rope that can withstand at least 6 newtons of tension. Otherwise, it's going to break. Similarly, your pin here needs to be thick enough that it can withstand these forces. Okay? So what you do is you do the static equilibrium calculation. You figure out what are the size of these forces that are involved, and then you can choose your components to be able to withstand those forces in the most cost-effective way possible. Okay? So that's my lesson for today, and I will see you in the Zoom room.